Hello? All right. Hello?
Hello.
I'm competing with a board game day, so we may start a little late here.
It's okay.
I see some of the class finishing the game. Any comments or questions on the previous material?
So you were mentioning like comments about the previous material. Are you still using the same reference you sent us last time, or is this a different reference from the course notes?
Um, which reference from last time did you mean?
Because last time you were telling us that you were using Peter Lax's
Oh
you
yeah, no,
know,
we're not using that at all. No,
yeah,
that would
I
be
figured
about the
so because I
shockwave.
looked at the notes and I looked at this and I didn't think there was any overlap anymore.
Yes. Okay, so I'll give you two possible maybe several possible references. So the book by Cato is very good. So, and some of you are going to do a reading course on that. I understand. So that's perfect. The other places I have some on archive. I have some ODE notes, and I do Laplace transform in that. There is also a book chapter about the things we're doing today, more or less, and that is called planar stability criteria for viscous shock waves, and it's in a set of Chime lecture notes, CIME, around 2007, and the appendix is about semigroup techniques. We're not exactly going to do that we're going to do a more self-contained version here that only uses Laplace transform. But there are many things in there. And then the other book is Paisley's semigroup book. So maybe the big ones are Kato, perturbation theory, and Paisley semigroup theory. This one you need. Sure. I mean, that's just very useful for orientation and the techniques we use. This one, less so. It gives it's a very nice book, and it will tell you about semigroup theory, but I'm going to state some results from semigroup theory, but I'll prove other results without using, I'll prove some weaker results that are sufficient for our purpose with no semigroup theory.
Okay.
So this is optional, but I mean, it's a great book.
Okay.
The archive that you mentioned, is that on your website?
I believe it's linked on my
Because
website, but I'm not
we
sure.
we went on the website and I think the link is like outdated, like it didn't
Oh,
get us anywhere anymore.
I believe it's both on Archive and definitely on ResearchGate.
Okay.
Definitely there.
Normalement, tu vas recevoir les informations sur les exposés, tout ça, surtout de guidelines, parce que sinon je vais sur le mailing list. Parfait, merci.
So those are some references. Hello? Okay, great. We have a new member. Hi. What was your name?
Remy?
Remy? I'm Kevin. Good. Glad to have you here. Okay. One note left over from last time. In some of the discussion, we were talking about the difference between the maximum real part eigenvalue in the spec. So here I've drawn the spectrum of a matrix L that is self-adjoint, so it has all real spectra. Notice the maximum real part eigenvalue is here. The matrix norm is out here because, of course, there are positive real parts and negative real parts. So the gap can be quite large. And this is very relevant because in a moment we're going to start talking about unbounded operators. And I'm thinking of the Laplacian in particular. So it is a positive operator, so its maximum real part eigenvalue is 0, but I'm not going to be starting with the operator norm. The operator norm is infinite. The spectra goes all the way out to negative infinity, so that's something we're confronting. But, okay. All right. Just a comment. Because I misspoke when we discussed this. Okay, so today we're going to talk about, okay, C0 semigroups and what I call the poor man's Proust theorem. Okay, so what this is I'm going to state some basic definitions that we're borrowing from semigroup theory. I'll state some basic theorems from semigroup theory, but then I'll prove a different, weaker theorem that doesn't need any semigroup theory, so it will be self-contained and does the same thing for us. Why am I doing that? Because the one that I prove will survive some of the adaptations we have to do later, and the other ones will not. So it's not, the method is not completely Oops, not completely inferior. It just gives a weaker result. Okay, so we're trying to transition to unbounded operators. And our goal is an inverse Laplace transform representation for e to the LT. So some linear solution operator. So first, basic definition, standard definition, we're going to take L linear and densely defined on X if one, there's a dense subspace or subset subset, which will be a subspace D of L in X on which L is bounded. And two, D of L is dense in X. Oh, it's not the most strategic word use. Okay, so for example, we have our operator that we're interested in. This one. What does it operate on? Well, X could be H2 and D of L would then be, say, H4. This is on the line. So this would then be, L would be bounded from H4 to H2, clearly. And it's nicely defined, makes sense on H2. We could make sense of it. We could define weak derivatives and talk about L2, but I'm not trying to optimize regularity. I'm trying to make it as simple as possible. So I'm going to work with pretty high derivative Sobolev spaces just to make it easier. Could be improved. Okay, and then L is closed if Xn approaches X star and L Xn approaches Y star, and these are both in X norm. Then
and bounded from edge must be bounded from the domain.
so bounded from the norm of the domain
So
to the norm of X. This is what I mean. So
is there a definition of norm of the domain?
yes, the graph norm would be the canonical one. Yeah. Yeah, to always make it happen.
So what is 2I? Is it DL of L? Is
2 is domain of L, D of L is dense in
yes.
X, in the X norm with respect to X norm. Okay, so that's a standard thing to, a standard setup for an unbounded operator. And then this is the rest, that if these two properties hold, then X star is in D of L, and L X star equals Y star.
Choosing the domain to be H4. What of H2?
When at H2? Well, I could also, I suppose. Let's see. Well, but I want, you see, I have in mind dTV equals LV. I have in mind this equation. I want that to very obviously hold in as a strong solution in L2. Yeah, I want it to make sense. Then if V is in H2, then LV is in L2. I don't want to go into negative spaces, but I could. You're right, without much trouble. Okay, so in our example,
Professor Zumbrun?
yes.
So I have a question about the definition of L. In part 1, you say there exists a dense subset D of L, which is a subset of X, and then in part 2, you have D of L is dense in X. Aren't those two pieces saying the same thing?
Oh, wait, yeah, okay, so dense in X. Yeah, you're right. It's just if. That's fine. And maybe this is parentheses, dense. I actually miscopied something. Okay, but it's worth a comment that, I mean, with respect to the X and R.
Okay, yeah.
Thank you.
Thank you.
Okay, so for example, if L, if L is A R bar dx to the R plus lower order terms, lower derivative terms, then it's closed from H, let's see, it's closed for X equals HR and D of L equals H2R, for example, what we're doing here. And okay, so if a R bar is uniformly invertible. So if we have a non-degenerate Rth order operator, it's always going to be closed from the obvious, with the obvious spaces. Okay. And I'm going to just show that because it's gives a chance to introduce some inequalities we use all the time. So the inequalities we'll use are Cauchy-Schwarz, the L2 inner product of F and G is of size less than or equal to the product of norm of F and norm of G in the HS inner product in the this is the HS norm. That's one. The other one is Young's inequality. This is just for numbers, which is AB is less than or equal to CA squared plus B squared over C, both with a 1/2. And then the last one, though, okay, so these are pretty familiar. The last one is what I call Sobolev interpolation. And this says that, I'll go down here. I'm going to say that dx f L2 norm squared is less than or equal to a constant times dx squared f L2 norm squared plus constant over 2 plus dx plus f. Actually, I want it the other way around. over 2c plus c over 2 L2 norm squared. And the proof is take the Fourier transform and use Parseval's identity. And so it's equivalent to say that 1 plus k squared f hat of k squared integral dk is less than or equal to 1 plus k squared integral plus f squared over f times c. Okay. Okay, and so so I'll just use, actually I just use Young's inequality. See, I'd rather, I wanted to start with this. I'm just gonna, this is equivalent. And I think I'd better stick with that to make this work out. Yeah, this is what I want. Now this is clearly just Young's inequality in the K terms. Okay, done. Okay, so that will allow us to do this pretty easily. To prove the, okay, so that's the Sobolev interpolation. Now, we'll just check closedness. So, by linearity, it's sufficient to treat the case xn goes to 0. We can always remove the x star, and Lxn goes to y star, and then we want to show then that I'm going to show Lxn goes to 0, which is in the domain of L, and so that's y star. So it's both in D of L and L of y star equals L of 0 equals 0. I'm sorry, L of x star is L of 0 equals 0, which is y star. Okay, so it's enough to show this. That right. That's right. No, I said this wrong. Sorry. It's precisely the reverse. It's enough to treat this case. Then I want to show that xn goes to 0.
Why don't you both in the opposite direction?
Sorry, what were you asking?
So why did you change the order?
I changed the order because this is the way I need to prove it. This is the tricky point. I guess I could change either one, but this way I can do it.
But why don't you do it for general? Do you need to have this 0?
Oh no, but it just makes it a little easier to verify that L of X star
Okay.
is Y star. If I know that Y star is 0 and X star is 0, it makes it easier to justify both things. So it means all I have to show is this. I only have to show one thing instead of playing around with other things. Yes.
It's different formulation should imply that X star is in the domain.
X star is let me see if I've got this right. I'm subtracting. I see. Am I doing this? After all, doing this backwards. Let's see. Oh, yes, indeed, I did it back. I had it right the first time. You're right. You're right. Otherwise, I can't. Yeah, it's all awesome. This is what we need. Yeah. This we can achieve, not the other. Yeah, we'll show that. Yeah, we'll show that then. That is what we want to know. Yeah.
Essentially, you have to show that Y star is 0.
Yeah. Yeah. You show why starting this. This is all, or in other words, LXN goes to YN goes. And this I do just by
Is this a proposition? Or a definition?
no, this is a proposition. So I just want to say that let's see. That LXN
E bar are close.
For the
You are moving from that path, right?
no, not for yeah, for an L like this. Yeah, for an L with non-degenerate first order term. And what I just want to use is that LXN is bigger than or equal to the min of A bar times dr x xn in L2 plus lower order terms. And then I'll use Sokolov interpolation that I just was demonstrating to get AR dxn L squared plus a big constant times xn L2. And this will, okay, and this is, this goes to 0. This goes to Y star in Y star. And therefore, I'm going to get a in X, and therefore I bound the HR norm of X. I bound the X norm, the L norm by the limiting L2 norm. The H the X norm, or the D of L norm, which is the R, this is to the R, sorry, of the limit by the X norm of Y star. That tells me that I'm in the domain of it by properties of weak derivatives. Right? If I approach weakly and I have a bound on the norm, I have convergence in the higher norm space. So I converge to an element of D of L, and let's see. I'm tying myself in knots, but I actually, so I think I'll stop there. This is not very hard to do, but I'm finding it hard. And we actually, in a moment, I'll give you, there's a better theorem that says it's almost always closed, which I'm about to give. So let me pass from this to the other one. Sorry, this is not difficult, even though I'm having some difficulty. Well, okay, so that the class of operators we're going to look at are closed densely defined. So we replace finite bounded L by closed densely defined. And this is now going to allow us to treat unbounded operators. Okay, definition. The resolvent operator is lambda minus L inverse from X to D of L, wherever it is defined. And the resolvent set, rho of lambda is rho of L is the set of lambda such that lambda minus L inverse is defined. So we've got a surjective and injective map, lambda minus L, and bounded. Bounded from from X to D of L. So it's actually, in our case, it's gaining two derivatives and it's still bounded. Okay, now this one is really not difficult, but if even a single resolvent point, if the resolvent set is not empty, then two things happen. A, L is closed. And that's really now become very easy because we have this way to hop up from X to D of L, and now it's just playing algebraically. B, D of L to the K is dense in X for all K. So these are the intersection of D of L with let's see. Well, it's the set on which L to the K is bounded. And all of those are dense for any power. And that's useful. Okay, but this one allows me to escape from my computation because it's almost automatic. So if you can't find any resolvent point, you probably have the wrong norm. And the graph norm is always right. The graph norm will be closed. Okay, so now we have a resolvent And kind of following the approach that we did for ODE at the end of the last lectures, we're going to define the spectrum. The spectrum sigma of L is the complement of the resolvent set. It's everything that's not in the resolvent set. So this replaces and enlarges the idea of an eigenvalue. Remember, for matrices, the resolvent set was everything except for the eigenvalues of the matrix. So it works perfectly. But this could be bigger. Okay. And now here's an important proposition, which is that the resolvent is analytic in lambda on the resolvent set. And in particular, that means the resolvent set is open. Okay, and this is because we can write lambda minus L. Okay, let's see. Let's start with let lambda not be a resolvent point. And we're going to look at, so that means lambda naught minus L inverse goes from X to D of L in bounded fashion. We'll write lambda minus L as identity minus lambda naught minus L inverse times lambda minus lambda naught times lambda naught minus L. So I'm just factoring out on the right lambda naught minus L. That's all I'm doing. And here, okay, this is a complex number, so it commutes. So I'm going to have a nice inverse if, well, this one has a nice inverse. And I will have a nice inverse if, let's see, a nice bounded inverse if I can do two things. I'm going to show so the claim is that this this piece, which is sometimes called the Biermann-Schwinger operator, has an inverse from X to X, bounded. And if so, then I will have that lambda minus L inverse is equal to lambda naught minus L inverse times this whole Biermann-Schwinger part. And this part is bounded from X to X, and this part is bounded from X to, well, let's do it this way. And this is bounded from X to D of L. So this will be bounded from X to D of L. And I'm writing the arrows backwards to show the flow of the operator. So that will be enough. But now I notice that this operator is even nicer than I need it to be. This is bounded from X to D of L. It's certainly bounded from X to X, because that's a weaker norm. And it's small as an operator X goes to X for lambda minus lambda not small. Right, because it gets multiplied by, so it's a small perturbation of the identity, so I can use Neumann expansion. So the proof of the claim is Neumann expansion, which gives me that the inverse of the Biermann-Schwinger part, this whole thing is identity. Actually, let me give this a name. I'll just call that alpha. Okay, so this identity minus alpha is just identity. It's the series, identity plus alpha squared, plus the infinite series, which is easily seen to converge. Done. So it's very, very standard, but still wonderful. I like this a lot. So we regained analyticity of the resolvent. That was something we saw for matrices just by explicit computation, but now we see it's much more general than that. It holds also with this unbounded setup. And then that we need to now discuss this, to divide up the spectrum. So more definitions. The point spectrum sigma p per point of L is the set of lambda such that lambda minus L inverse is meromorphic at lambda. Say near lambda. Okay, these are points that are not in the resolvent set, so there's no reason that they should be anything. And meromorphic means that it is it has at most it's analytic on a ball of radius epsilon minus the central point lambda, and has a pole of finite order at lambda.
So our hypothesis on L to derive all these properties was only that it was closed and densely defined.
Yeah.
That was a hypothesis.
That was the hypothesis, and so far we didn't use closedness anywhere yet, but anyway, as soon as we have some point in the resolvent, and otherwise there's not much to talk about by these techniques. So we'll always have that, or we start again. So really just think of densely defined and something that has some resolvent. So the right norm. Okay. Oh, this is a subset of sigma of L. So first of all, it's not resolvent points. It's a point that's not in the resolvent, but is meromorphic. The essential spectrum sigma essential of L is sigma of L intersect the complement of the point spectrum. So it's everything that's spectrum, but not point spectrum. That's a really easy definition, but operator theorists will have they have many subdivisions of essential spectrum, all interesting and important in different contexts, but it won't play a role here for us. So let's keep it simple. Yeah. And also in different contexts, there are different subdivisions that overlap. It can be very confusing. But okay. So we are okay. And okay, now here I will go outside the course and just refer to Kato, that when you have So at lambda in the point spectrum, so at a pole of the resolvent, we have that the residue at lambda, let's call A, call it A. Residue at lambda equals A of the resolvent is the eigenprojector. It's a projector. It takes X to be of L. And also the residue of lambda to the K, lambda minus L inverse at lambda equals A is L to the K of P of A. So it's the operation, lambda replaces the operation of L. And finally, the residue at lambda equals A of e to the lambda t, lambda minus L inverse is e to the LT, acting on the projector, the eigenspace of associated with A. So it's the range of P. So, and that could be infinite. I think the range could be infinite. But knowing that we have a pole of finite order means eventually these things disappear. So it means L, let's see, I think I said that. Said that wrong. No, that's right. Yeah. If I look at L minus lambda to the K, I think that's what I want to say. Yeah, sorry. Here we go. This is what I want. Lambda minus A to the K is L minus A. Okay. And that shows us that since this is a pole of finite order, eventually this will become zero residue. So that means some power of L minus A will annihilate the eigenspace, and so this is nilpotent. And so we recovered basically the finite dimensional theory.
here. We lost the view of the board and we're not hearing anything.
Okay, right in.
Okay, can you hear me now?
Yes.
Okay. At what point did you stop seeing the board?
The last stuff you wrote, Hilo Yoshida, that stuff we did not
Oh,
hear.
okay.
Everything else I think we did.
Okay, good. Then we lost essentially nothing. So I'll repeat. This is the Hilo-Yoshida theorem. It says that this condition that the resolvent operator, now considered as an operator from X to X, which it certainly is, if it's just bounded by C over, okay, let's see, let me just copy this now. Over real part of lambda minus some theta. And the same for lambda minus the adjoint. If these both hold for all lambda, real part of lambda greater than theta, then we get a nice existence theory. We get a e to the LT with bounds less than or equal to C, e to the theta t, and continuity, e to the LT x is continuous in time. Oh, let's put a V here for V in X. So a specific V. So it actually gives you an existence theory, a nice linear existence theory with an exponential bound like the one we started with before. We're actually, okay, this is just for orientation. We're not actually going to use this because we're not going to need to prove all these bounds. So we certainly can do it easily. We'll go a different way. Okay, that's one. And okay, and this is called a C0 semigroup. Okay, now notice for matrices, we had a much better bound. We had C over the modulus of lambda. This is just bounded by the real part. So that's a much weaker bound. And when you have the stronger bound, you get an analytic semigroup. It's much more powerful. And you can
So
okay.
theta is unknown or it's
Theta is just whatever you can prove this bound for. And in a moment, I'll show how you can prove bounds like this. Because we haven't done that in the unbounded setting. Well, it doesn't need to be positive. It's just real. Theta is real. Any real. So okay, so let this hold, then, or in fact, yeah. Yeah. Then we have this. And I'll remark star is necessary for C0 semigroup. That's the other part of the Hilo-Yoshida that's very nice. So star without the adjoint, just the first part, that's necessary. And this with the adjoint bound is sufficient. And usually, so in our case, the adjoint operator looks almost exactly like the forward operator. So if you can prove one, you can prove the other, and that's usually true. All right. Okay, next one is the inverse Laplace transform formula. And this says for a C0 semigroup, e to the LT v of 0 is equal to the formula that we've just been deriving. So a C0 semigroup with constant theta, with exponential growth theta, we will have gamma minus I infinity, gamma plus I infinity, e to the lambda t, lambda minus L inverse v of 0 d lambda. And this will be a principal value integral, and the notion in which its principal value is it's the limit as r goes to infinity of the integral from gamma minus IR to gamma plus IR, exactly as in the finite dimensional case that we did in some detail. And this will hold for all gamma greater than theta and t greater than 0. So this actually expresses a limit, right? There's says a certain limit converges to the solution operator that was defined here. And it's not defined using the inverse Laplace transform formula. It's defined some other way by the Hiller-Yosida construction. By the implicit Euler scheme. That's how it's done. Okay, so it looks nothing like this. And yeah, there's one more important. And v of 0 has to be in d of L squared. It doesn't work always. So in the finite dimensional case, we had no issue. And we can see that there's no issue because the domain of L squared is the same if L is bounded from X to X, and it's a matrix. L is bounded, so the domain of L squared is X, which is the domain of L. There's no discrepancy between those. So here's where the unboundedness comes in. Okay, so a strategy is to obtain bounds from, I'm going to always call this ILT, even though it's not just the inverse Laplace transform, it's the inverse Laplace transform formula for the solution operator, but I just denote it this way. Obtain bounds from the inverse Laplace transform formulation depending only on X. And if you have those, well, then you can then use density plus continuity of the solution operator. Or not continuity, plus boundedness. The boundedness that I'm talking about is here. I have from the beginning, this is true in the X norm. This is from X as an operator from X to X. I get this bound. That's the Hiller-Yosida bound. So if I have this, I can use density argument. I can go in, and I know that d of L squared is, I know from these, implicit in the existence of these bounds is that there is a resolvent set. So, and it's non-empty, so it's a nice, so d of L to any power is dense. D of L squared is dense. I need that in X. So if I prove some estimate for things just in d of L, but the estimate is independent of the d of L norm, I can extend to all X by continuity and density. This is the continuity.
So what's written on the blackboard, that up there, the ILT
Yes.
formulation, this is a concept, you can prove it from, you see that?
You have to do more. No, you have to do a few more steps. And I'm going to show you effectively those steps in proving, I'm going to prove this formula in a different way,
Not from here.
not from here. And at the same time, you'll see how you can extract bounds. Let me state one more bound for, oh no, let me not state one more bound. Let me stop here. Let's take a break. We come back in 5 minutes. I'll tell you one more amazing fact that we're going to prove weaker things in easier ways. I won't go into all the theory, but prove something weaker but good enough for us. That's the plan. Okay, so 5-minute break. Looking at them, but they're here. They're looking at.
Oh.
Yeah.
Yes, for us.
Yes.
Equipment here.
Yeah. This room is very nice.
It's
Like-
better than the other room.
Oh, yeah, there's a big.
But
It's a big, and here we have
Like,
windows on the.
why in the fall didn't we have your lectures here instead of going here?
Oh, because it's
Amazing.
difficult, it's not university,
Just
we're not, it's different.
jacket like here.
No.
But there's no.
Oh, no, because they have the whole thing. Mhm.
Well,
Remy, are you also here for this semester, special semester, or are you just here in any case?
Yeah, I'm here as a postdoc, but not for this thematic program.
For this one?
No,
not for this one.
Not for this
Oh,
one.
okay.
I'm just curious.
General. Okay.
Yeah.
Okay.
So is this operator L is like a general operator or it's like specific operator with like some nice operator?
Could be general, closed, densely defined operator.
Okay, so
So then we make these assumptions.
so it can be like a local operator or also not like non-local operator.
Yes, it could be a non-local operator, I suppose, yeah. Yeah, but it might be, but the next things I do, where I actually prove these bounds and things, that would be a lot harder, I suppose.
Sure, yeah. Because I'm working on like non-local PDEs, and the operator is like what we call the fractional Laplacian.
Okay,
Yeah, and it also has nice properties. And
that's really quite interesting, and yeah, that makes me want to see, yeah. Now I'm gonna pose you a challenge to prove some exercise. Get to the point where I make the estimates, and then we go, hey, yeah, I don't think I'll examine it in here, but we can formulate it. That's a good idea. On this sheet, I'm going to. Maybe.
okay.
They told you it's working? Okay, they told you it works, yeah, now. Wow.
serious. Great. Oh, that's wonderful. Okay. Yes.
Okay, so the returning, you can hear me?
Yes,
Oh, yeah, thank you.
yes.
Oh, we still, oh, okay, I'll just wait a minute. I'll wait a minute. That's important. As long as he didn't start another game. Sorry, why did
I think like Erdos would say that like a mathematician is a machine that converts coffee into ideas. But I think Erdos was.
I met him. He came to my undergraduate class and palled around with us. That was really fun. Anyway, okay, so last famous theorem. This is Proust's theorem, or the Proust-Gerhardt theorem. And this says for a C0 semigroup on a Hilbert space X, if we have lambda minus L inverse is less than or equal to a constant for real of lambda equals theta, and lambda with real part of lambda greater than theta is contained in the spectrum, sorry, in the resolvent set of L, then e to the LT from x to x is bounded by c e to the theta t. Okay, so that's fantastic. Now we got rid of, we don't have to prove, in Heliocida, we had to look at all the possible, bound everything carefully for all lambdas. Here we just need on one point. So it's what we would, it's what is suggested by, but doesn't follow from this implicit, inverse Laplace transform formula. It sort of looks like if this is bounded everywhere, we should just have exponential decay, pulling out the e to the if gamma were theta. Okay, this is, I should have really stated it with a gamma. I think, yeah, let's make it consistent. With what I wrote before. Yeah, there. Okay, so
So upstairs you had the gamma larger than theta, right?
yeah, I had gamma larger than theta, but here we don't need that. And notice also though, this bound, if I try to take gamma equals theta, then the gamma is the real part of lambda by my definition. Yeah. Okay. So if I chose theta to be gamma, this would blow up. This isn't a bound on the line theta. So I'm assuming a little bit more. Yeah, I'm assuming I'm actually a little a little to the right of theta to get that to have boundedness. And yeah, anyway, this states, in fact, the full Proust theorem says that actually you get better, you get for some epsilon greater than 0. So you actually get more. The full theorem is even stronger. Okay. Than one might expect. Okay, but we're not going to go. There's one clue that this is a little subtle. Here's a big clue. What could that have to do with it? That we suddenly need X to be a Hilbert space. It means there's going to be some, some fancy footwork in the proof, and there is. Now there are some extensions to Banach spaces, but they have weaker statements. I mean, weaker conclusions. Okay, and okay, so now what am I going to do? I'm going to not give you all the semigroup theory. Instead, I'll verify the inverse Laplace transform formula, and from it, I'll prove a really, what I call a poor man's Proust theorem. So something that's not as good. Okay, so.
So Proust, he lived in when when
Uh,
was the year of this theorem?
Jan Proust still, I am not.
It was
I mean,
after
it's not so long ago, these things, that his career.
Helios,
After what?
after Heliocida.
I believe so, yes. These are, yeah. And was still active. So even though this theorem, I guess a lot of other subsequent theorems by him were about Banach space versions. Okay, so instead, let's proceed as in the finite dimensional case. Let's assume the existence uniqueness theorem with theory with, so which I'll denote the solution operator as e to the LT again. And it's a bound from the space X to the space X. And this tells us, just as before, there exists a Laplace transform. V check, and it's also in the space X, and it's defined by V check lambda is e integral from 0 to t, e to the minus lambda t, v of 0 to infinity, lambda t, v of t, dt, just as before. And it works exactly as before. It's a absolutely convergent integral. Makes perfect sense. This is for any gamma defined as real part, of lambda greater than theta. That's what we need to make this converge. Because then we know that this is growing no faster than e to the theta, e to the theta t, and this is decaying like e to the minus gamma t. So this exponential decay beats that exponential growth.
It's gamma. Oui, gamma.
Gamma is the real part of lambda. So the modulus of this term is e to the minus gamma t. e to the minus gamma t. So if I just do a crude bound, this is bounded by e to the theta minus gamma times t. And theta minus gamma is assumed negative. So this is an exponentially decaying integrand, and so everything works. Okay. And in fact, I also get the inverse Laplace transform v of t is equal to pv e to the lambda t, and here we have gamma minus I infinity, gamma plus I infinity, v check of lambda, d lambda. It's not the same. This is just inverse Laplace transform of the v, of v check. And that one is the solution formula. So this is weaker, this is less. So we want that lambda, dt of v check is equal to lambda v check, so of lambda v check of lambda minus v of 0. We want this is the thing we want to have in order to convert this into the solution formula. Okay, but so we have to look at how does that proof go? Well, we need e to the minus lambda t dt v t 0 to infinity. We need to integrate this by parts. Okay, so first of all, we need that this makes sense in the x norm. So for that we need v in d of L. So actually, I was a little careless when I said we want an existence and uniqueness theory. I want it for x. I also want it for d of L, d squared of L, for any. I want to know that it extends to higher derivative norms as well. And as you know, we usually get one with the other. Okay, so if I have that, then I can integrate by parts. This has an actual derivative that makes sense in x, and I can integrate by parts, and I get okay, so I get lambda e to the minus minus lambda e to the minus t v of t from 0 to plus infinity, and this one vanishes by the exponential decay. I'm left with there's no lambda here. Sorry, there's no lambda. It's just this, and I'm left with negative v of 0. And then minus the negative, so plus lambda. So I'm integrating e to the lambda t, e to the minus lambda t, and I get e to the minus lambda t again, and v of t, dt, and that's v check of lambda times lambda. So I verify the formula exactly as before, but I need another assumption. That's because of the unbounded operator, in order to make sense of this. So that's one step. So now if also the spectrum of L, if lambda such that real part of lambda greater than theta is in the spectrum of L, and lambda minus L inverse is like what else do I need? No, that's all I need. Then I know that V, I know from the equation, okay, dt V minus LV check is equal to 0, but this one is lambda V check minus V of 0. This one is minus L V check, and again, that's because I assumed I was in D of L, that I can pass the L into the integral, and that's 0. But that's now, and this is exactly what we did before. So now we have lambda minus L V check equals V of 0, and V check is equal to, resolve it, applied to V of 0. And substituting in to the inverse Laplace transform formula, into the inverse Laplace formula for V, I can just substitute in lambda minus L inverse V of 0, and I have what I wrote up here. But important difference, I have this in, the convergence is in L2 of time. L2, that's what you get from the inverse Laplace transform. And here I stated but this is a pointwise convergence result. It's for every fixed t greater than 0, this holds pointwise. So how do I get to pointwise? Well, I'm actually going to prove it for V of 0 in D of L squared. We'll get absolute convergence. Well, we can get pointwise convergence. So by the same method we're going to use to get a bound. So far we've verified this only at the L2 level. Why L2? Just because I've cited Fourier transform theory to get this, right? So I have something that's in L1 intersect L infinity. It's in all spaces, but I took the Fourier transform, basically, by taking the Laplace transform. Now it's in L2 intersect L infinity. And in taking the Fourier transform, the inverse Fourier transform, you need to do it by a limiting process. You truncate it. That's why we have the PV. And then you use Parsifal's identity to get a limit, to get control of the remainder. And that left us with, it's only defined in L2 in the first place. I only have this inverse in L2. L2 in T, from 0 to infinity.
The field in the
Oh, okay, so I'm suppressing the X variable. It's part of the function V. V is assumed to be a function on.
what to estimate anything in space?
Only the HS norms in this, so far, in this setup. It's only the HS norms.
It's supposed to be true.
Yeah.
So it's Laplace in infinite dimension.
It's only Laplace.
Laplace in time, but it's infinite dimension in X.
Let's see, Laplace in time.
Laplace transform.
Laplace transform in time only. Yes, there's no X. Yeah, there's no X transform. Yeah. And I only have one dimension, one spatial dimension, and all the coefficients depend on that dimension. So I can't Fourier transform that one away. I have to keep it, but I'm keeping it in a very weak way here. But these are some basic results. We're going to keep making things more complicated because, in fact, to get where we finally want to go, I'm not able to do it with ignoring spatial effects. So we will eventually put space back in explicitly.
square just because you need one derivative?
That would be one way to look at it. It's actually, I was gonna, yeah. I'd like to have a time derivative. If I had convergence in L2 and in L2 of the time derivative, then I Sobolev it. But it gets a little subtle, so I don't want to do that. This straight term v of 0 in the key formulation here. Let's see, what was the formulation? Oh, just basically that this one. This term gets in the way of simple things. Of what you would like to do. Yeah, but you can do it that way. That's a nice way to do it, I think. But yeah, it gets surprisingly involved. Since I'm going to do the other thing anyway, I thought I would skip that. But the two proofs are very similar in the end. You'll basically find there's a piece that's not absolutely convergent. If you do that, it's not obvious what to do with it, but it's explicit. It's just involving. This is just a constant, so you get some Laplace inverse that you know from a table. It's a function, and then the rest you estimate in a different way. Okay. Okay, but I'm going to stick with this. Okay, so yeah, so I know that this is true in L2, and it converges to the genuine solution. So if I show that this converges pointwise, by any means, I know that it's going to converge to the correct solution. So I just have to look more closely at this formulation and verify that the integral actually converges pointwise. And then I know I don't have to worry where it converges. I've already shown that in L2. So that's a key point. And now, let's see. Okay, so now we're going to go toward estimations. So we'll do pointwise verification plus estimates. Proust type. At the same time. It's just as convenient. So the key idea is the resolvent identities. So by the way, when we did the finite dimensional calculations, when L was a matrix, we still found in integrating this, we got some funny terms that didn't converge absolutely. And we had to do those explicitly. And you'll see something very similar popping up here. Okay, so here's the resolvent identity. So it's lambda minus L inverse is equal to L over lambda minus L inverse plus identity over lambda. And this is just an algebraic relation. If I multiply both sides by lambda, then I see it. I get lambda minus L inverse is equal to L lambda minus L inverse plus identity. And that is clearly true because if I subtract this from the left-hand side, I just have lambda minus L against its inverse, and that's identity.
Just up.
Up here?
No, oh, yes.
Oh, sorry, finite dimensional calculation. So in the previous lecture, we did this explicitly for the matrix case, and you could even think of a scalar equation. So just a real number. And then, so this is L. And then lambda minus A inverse, well, that's what it is. It's just a number. And if we want to integrate e to the lambda t over lambda minus A, well, we really have, so that's, it's not absolutely convergent, and you need to estimate it. And the way I suggested to estimate it was to break this into, okay, 1 over imaginary part of lambda minus 1 over imaginary part of lambda squared. So if you pull out, if you take the difference between this, oh, and I pulled out all the real part is constant, don't forget. So if I take the difference, this is really, yeah, okay, anyway, I'll get something of order tau squared, where tau was the, I'm using notation from the previous lecture, but it's order of the imaginary part squared. That's now, that's absolutely convergent. So that one is fine, and this one is explicit. It's a delta function in time. That's located at 0, so it's 0 in L2. Yeah, so yeah, okay, so that's kind of what we're mimicking here. So this was all an aside. Let's keep this go out here. That's the formula. And look at the resemblance. I'm pulling out an explicit term, and then the rest, it has a little bit better decay. Okay, and so this one converges. Okay. And then what I'm going to need to do, though, I actually need to do it twice. I only needed to do it, I needed to do it once for bounded operators because they decay like 1 over the imaginary part. I had an extra decay. I don't have that here. So I use it again, and I bound. So the part that's not constant was L over lambda, lambda minus L inverse. And so I want to use the resolvent identity again, and I get that that's L, let's see, L squared over lambda squared, lambda minus L inverse, and then plus L squared over lambda squared, plus identity over lambda squared. With an L, sorry, L over lambda squared. Okay, both of these are going to be absolutely convergent as long as I'm in D of L, this one, and here I need to be in D of L squared. So we'll write it in 3 pieces. So the integral from, I'll leave, okay, so I'm going to pull out e to the gamma t. And then I have principal value integral d lambda of 3 pieces. So I have e to the I tau. Okay, now lambda minus L inverse L squared over lambda squared. I'm going to need more space. E to the I tau t, e to the I tau T times lambda times L over lambda squared plus e to the I tau t identity over lambda d tau.
Replace the formula into where, into which equation?
For the inverse Laplace transform
Oh,
formula,
up there.
this one,
Mhm.
I'm just rewriting it in terms of lambda equals gamma plus I tau. And now it's integral from minus infinity to plus infinity. It's simpler. That's just an integral in d tau. It's really just the imaginary part that's changing, and the real part is fixed. So I've pulled out the exponential growth or decay coming from the real part. And in order to get a Proust type bound, this is all I want. I want to show that the rest is bounded. That's all I want. Just a bound. And by the way, at the same time, that will give, I mean, to get a bound, I have to have pointwise convergence as well in getting this bound. So I want a bound for fixed t greater than 0. I want a bound. Or let me put it a different way. T greater than or equal to t naught greater than 0, and t naught will be fixed. I'm going to get a uniform convergence and a uniform bound. I claim these first two terms are easy. Don't forget that u of 0 is in d of L squared. So wherever I have L powers of L appearing, I'm going to apply those to u naught, and I get a nice bound, but I'm bounded by the d of L squared norm of u naught. So I'm allowing myself to lose information here.
But U and V is the same? U,
Sorry. This is V. Yeah. Sorry. Yeah, V of 0. Mhm.
so you had a formula upstairs
Mhm.
and you replaced lambda minus L by using twice this
Yeah,
trick.
nice trick.
Okay. And that allowed you to transform it there.
Mhm.
And then you gain by having the lambda downstairs.
Yes, I gain convergence
Good.
because lambda is gamma, which is bounded, plus I tau. So yeah, so it's always it's basically of size. So if I have 1 over lambda squared, that's of size tau, better than tau squared, bigger than tau squared, or like 1 plus tau squared, and that's fine. So these two terms are bounded by a constant times v of 0, but in the d of L squared norm. And here I'm estimating, and I'm working in the X norm. I want to converge in the X norm, and I want bounds, X norm bounds on the solution operator. Okay. So far, this equality is only known in the L2 of 0, L2 of time. But now I'm going to show that the thing that these integrals actually converge pointwise, and from that I'll have equality pointwise in time. Okay, so it's just now it's just estimates, and I want to both. So if I'm estimating the tails, I have a uniform convergence, and now I have only left one thing, and this is explicit. It's the same one, essentially the same one that was left over in the what did I put in the finite dimensional case, and that was my suggestion to break it up as 1 over tau, 1 over lambda plus some higher order term. This is explicit, and you can estimate the convergence rate. it's basically converging to a delta function. I'm sorry, am I saying this right? This one is this one's a heavy side function at 0, but it's bounded.
Sorry, are you integrating over with respect to with respect
Tau, with respect to tau. So this is really 1 over gamma plus tau. Yeah, so I can.
because I see d lambda here.
Oh, I'm sorry. That's sorry. Yeah, I'm putting a d tau at the end of everything. We're trying to. So this should have been with the big right there. Now it's right. So I have 2, and one was wrong. Thank you. Yeah, now it's right. Yeah. Okay, so this one we get both a bound and a uniform convergence pointwise in time. Actually, it's uniform for all these t's if you look at it closely. And they're bounded. So what I get from this, I don't get what the Proust theorem told me. I got e to the, I can bound the x norm of the solution at time t by e to the gamma t times the value, the x norm of the initial data. Here, I don't have that. So here, what do I get? I get so this is my poor man's Proust theorem, and this says e to the LT v of 0 in x norm is bounded by a constant times e to the gamma t times v of 0 in the d of L squared norm, which that's a loss of 4 derivatives. It's not a good bound. Okay, and this is under what hypotheses? Well, it's under the same hypotheses as the Proust theorem. So we have that lambda with real part of lambda greater than or equal to gamma is in the spectrum of L, and lambda minus L inverse in the X norm is bounded by a constant on real part of lambda equals gamma. So on the contour. Okay, so that's what we get easily. But we also get we also verified in passing, we verified the inverse Laplace transform formula pointwise for V in L squared. So that one was sharp. That's, you don't get more from the semigroup theory. You get this. Okay. And yeah. And if you work hard, you can actually recover the full Proust theorem for Banach spaces. So without the Hilbert space assumption, by doing some, just working with this and doing some contortions, basically working in the L2. We don't have losses in L2. In L2, it's good. It's bad pointwise because yeah, that's basically the idea. There's a bit more, but I don't want to work hard. I want to work easily. And also, there's no point because recall regarding the loss of derivatives. So here, L squared is like taking 4 derivatives. So that's not such a good bound, but variation of the equation was dtv minus lv equals dx n of v, where this was order of v squared. Variation of constants, the inhomogeneous linear solution formula says that v of t will therefore be e to the lt v of 0 plus integral from 0 to t of e to the lt minus s, and then this dx n of v of s ds. So I just want to point out that we already lost a derivative. Just by separating things into linear and nonlinear parts. There's an apparent loss of derivatives that's not, and this often happens. It's not really there, but it's not really there because of the nice nonlinear structure that we don't see here. So the point of view here, since I'm not worrying about optimal regularity, is I've already lost one, 3 more, doesn't matter. It's like the h to the 100 of some earlier talks this week. I just want something that works, and I'm not going to worry what the smallest one is. Okay, so, all right. So next time, we're going to show somehow you have to repair this by some nonlinear argument, and I'm going to show a method to repair lots of derivatives. But before I do that, just in closing here, how about verifying the assumptions? And by the way, the nonlinear argument will be very much along the lines of what I do here. So we made some assumptions. Maybe I should stop here though and just ask, so it's clear what I'm stating. Yeah, I get the Proust theorem, but with loss of derivatives, but it's very low tech, so that's what you get out of it. And there's more though. I need the freedom to take little pieces of the contour and move them around and still have these kind of estimates. I don't have any version of the Proust theorem for a contour that looks like this. Only one kind of contour is allowed, the straight up and down kind. And we know by Cauchy's theorem, we can move contours all around, and that's a big part of getting estimates. So we will need to be more flexible. This method is more flexible, even though it gives worse bounds. All right, so how about this bound? Yeah, there we go. How can I get that bound? Well, let me write this out. So I have dt v plus equals negative a bar v dx minus dx squared v. I'm just going to take an energy estimate by multiply by v transpose over 2 and integrate. So I'll get the HS norm squared over 2. Let's just work with L2. I'll just do an L2 estimate, and the HS norms work the same. So L2 norm dt. That's equal to dt of v against inner product, L2 inner product against dtv. And that is v against the things shown here. So it's v dx negative a bar v minus dx squared v against dx squared v. This one we know integrating by part, that's a plus. Integrating by parts, we get negative dx squared. In L2 norm, that's a very good term. This one we get by Cauchy-Schwarz, order of v dxv. And by Sobolev interpolation, this is less than or equal to negative dx v squared over 2. So I'll give up half of this good term, plus a large constant times v squared. So I can get rid of the, let's see, is that what I wanted? Yeah, that is fine. Yeah, that's what I want. So this gives me, now I just drop this term. And I have a nice growth bound in the norm. I have that dt of vt squared over 2 is less than or equal to a big constant times v L2 squared. Actually, let's call that big constant theta. And now that is equivalent to v squared of t less than or equal to e to the 2 theta v of 0 squared, which is equivalent to v of t less than or equal to e to the theta, 2 theta t, e to the theta t. And here I'm using Gronwall, v of 0. That's exactly the bound, the kind of bound that we wanted, but we're not using the matrix norm, the matrix operator norm, but the numerical range. That's what we're using, essentially, to bound the largest eigenvalue. And so that's what an energy estimate does, and that's what substitutes for unbounded operators for the matrix norm. The matrix norm is unbounded, but it's all in the negative side, so that's helping us here. Let's see, do I have long enough? Perfect. Okay, I have one more to show you. I might give an exercise. That was the parabolic case, the hyperbolic case with A bar symmetric. Reproduce a bound. And here you have to be more careful because you don't get a good term at all. You get only a not so bad term. So what you need to show is that the term negative v dx a bar v is less than or equal to theta v squared for some theta. And that's some integration by parts tricks. And you use the symmetry to get it. So it also works fine for hyperbolic operators. And that's the difference between, so when using strictly parabolic operators, one could use analytic semigroups. Everything looks nicer and is simpler. But I have in the back of my mind, I want to treat relaxation systems, which are hyperbolic. I want to treat degenerate viscosity, like the actual real Navier-Stokes and MHD and so on. Those have degenerate viscosity, so it's as if they have a hyperbolic part and a parabolic part. I need something that works for both. So I don't want to use everything that I have here in this simple case. I'm trying to analyze our simple case in a way that translates over to the complicated cases that we really want to apply it to. Okay, last point is, okay, that was one. We made two kinds of assumptions. That was one, and the other was about resolvent bounds and resolvent set. Okay, so resolvent bounds mean we look at dt minus L, v equals f, and we want to get two kinds of bounds. We want v less than or equal to, in the x norm, less than or equal to a constant times f in the x norm. But that's the kind of bound we assume on a contour. That's one kind. But we also need that v in d of L norm is less than or equal to a constant times f in the x norm for lambda in resolvent set. So you have to get both. How can you get both? How can you get one? So here's how you do it. Actually, you do it in very much the same way. Energy estimate. But now, okay, so it's lambda v equals negative dx a bar v minus dx squared v plus f. That's the only difference. This is d lambda. Sorry, thank you, d lambda. Not d lambda, it's lambda. Yeah, lambda. Yes, lambda.
So you,
But I'm thinking of it as dt, of course. Yes.
here it's with V hat, opposite hat.
Yeah. 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 But that's just, yeah, relabeling it. Yeah. So let's put checks everywhere
Check.
so it matches. That's better. But now I'm going to take an energy estimate. What I want is to take real part of lambda v check, lambda v check, v check, which is real part of lambda v check squared. Okay, but then that is equal to the real part of v check against negative dx a bar v check minus real part of dx squared v check against v check plus v check f check. And yeah, I don't even really, I don't much need the real part. I could just bound this by Cauchy-Schwarz. This is less than or equal to a constant. Whoops, check, v check, dx v check. And this is dx, this is plus, it becomes minus dx squared v check. And this one is just bounded by v check f. And now I just observe that, again, Sobolev embedding, Sobolev interpolation, I mean, I can distribute this between, I can make this less than or equal to a big constant times v check squared, because I can absorb this into half of this or all of this, and the rest just L2. And then plus v check f. So if real part of lambda is bigger than this constant c, I can absorb this term into the other term. And also I'll divide the whole thing by norm of v check. And I get the v check is bounded by f over real part of lambda minus c. That's the Hillo-Yosida type bound. And I got it without much trouble. So what's my theta? Well, my theta is just this constant that came through the basically commutators, like derivatives of a bar and things like that. So, right. So that's how you do it. So it's actually, even though you might have thought that, this is a great theory if you have those assumptions, but where do you get them? Well, you see that it's not so hard to get these. Of course, you need to then use the previous one to generate, that's just an a priori estimate. You have to do the short time existence uniqueness, but that's the key to the bound part. And that's where I'm going to stop. Oh, no, I do want to mention, well, this was a bound, I need this one. I did this one. I need this one. How do I get the D of L bound? So that means D of L here would be H2, but let me get H1 and then I could repeat. Okay, let me just show how to go up by 1. Let's see. Oh, actually, no, I could just, yeah, let me go all the way up to H2. And this is instructive in 2 ways, you'll see. Okay, so if I want to get V check in D of L squared, or just D of L, let's okay. That's V check H2. Okay, but now I do have the equation, right? I have dx squared V is equal to, well, lambda V plus A bar V with the dx and plus F. So I immediately have dx squared V is less than or equal to lambda, norm of lambda, V, plus V, a constant times V, Vx, plus, constant times the H1, constant times dx V plus V and plus F. And I can use Sobolev interpolation again to absorb that over here at the cost of a further constant here. I've already bounded this L2 norm, and F is another thing that I am allowed to bound. That gives me a bound. I get dx squared V is less than or equal to a big constant times the imaginary part of lambda. Because the real part is being held fixed here. So let me not worry about that. And then times F. So this is the kind of bound you get in D of L, and you can upgrade by differentiating the equation and repeating to get to D of L squared. It's interesting though, for each application of L, you lose control by a power of modulus of lambda, which is the imaginary part. So this is not going to be uniform on an entire contour, on the vertical contours that we're integrating on. It's just not uniformly bounded. Whereas for the finite dimensional case, they were. It was in fact bound, it went to 0 for large tau. It was 1 over the modulus of lambda in size. So that's which exactly, yeah. And taking a derivative is like applying L, that does nothing in a bounded operator case. So we're in a lot worse situation. And that's why we're going to all this trouble with the resolvent identities and so on to trade things in. Because it's just, you might like to prove an easier theorem that says, suppose the resolvent is bounded everywhere on the contour from X to D of L squared, well, then you would be done. But that never happens. It's not even bounded from X to D of L, as you see. Okay, so stop there. And next time, I'll show you how to repair this loss of derivatives. And it's going to be by energy estimates that are just very much similar to these. Because notice, we didn't lose a derivative here. And that came by, well, in the strictly parabolic case, we didn't lose a derivative because we're actually gaining derivatives. It's a smoothing operator. You just don't see it so well if you're careless, as we were careless. But in the hyperbolic case, you truly lose a derivative if you divide it up into linear and nonlinear parts. And why we don't lose a derivative is there was a diagonalizability assumption, which is related to Friedrich's symmetric operators. And so, I mean, you can't do it. There are assumptions on A bar. Either I assumed it was symmetric here for ease. Second exercise for extra credit would be, what if it's diagonalizable or symmetrizable in a smooth way? And then you can still get the bounds. Okay, that's it. All right, thanks for bearing with me for the full 2 hours. That's our snow. You have to pay for your snow day.
So you energy estimates are kind of easy to do, right? I mean,
yeah,
but they are important to make you use the other approach.
yeah. I mean, I need something. So if not that, I need to do something else. And one of the things you could do is apply the Hilliard-Yosida theorem, but that seems like pretty heavy machinery to put in when you don't need to. Even though, I mean, it's good to know it exists, and it makes arguments a lot shorter if you just appeal to that. But let's see.
Same kind of estimates as the Yoshida.
Yeah, actually, in the Yoshida theorem, the proofs involve these resolvent identities and carefully, it's just the same. Yeah, yeah. And it's inspired by that. But why am I doing it this way with loss of derivatives? Because I'm going to later do this estimate on one piece of the contour and not other pieces. And for that, I can't appeal to Yoshida. I can appeal to these direct bounds. So I'm kind of saving some time, really.
Your problem is to show stability, so you will going to linearize near the solution or near a particular.
Well, we've already effectively done that, right? We're linearizing around an equilibrium, and our V is the perturbation from the equilibrium. And there's a linear part and a nonlinear part. Right now, we're trying to show how to get the linear decay estimates that we need from spectral information only. So actually, we just finished that part, and and then except I say this is what we need, but I haven't shown that because we lost a lot of derivatives here. I have to show that we can get them back. But it turns out energy estimates are good for that too. And but maybe there's another. Sometimes for some problems that have to do with shock waves, when they have actual discontinuities, this is now a boundary value problem effectively, and it's not a homogeneous one. There's usually a forcing on that boundary value. And so that makes it a little harder to set up a semigroup formulation. You can do it by subtracting out the boundary condition and turning it into an interior source somehow, but it's a bit cumbersome. But these kind of things would still hold with the inhomogeneous source just included in the Laplace transform. So I find it convenient. It's more flexible in that way a bit. In the end, it's all the same. You see the same things coming up. You have this principal value of e to the lambda t 1 over lambda. Every time, it's in every proof. And either you get it by explicit matrix calculation or by a resolvent identity, but that's the key to these estimates. Any other? I did have a question before the break. What if I had a non-local operator, like a fractional Laplacian? How would I then get such bounds? And I will mention that. So I used energy estimates here, but in fact I didn't need to really, because this is ODE. It's really a boundary value problem with the boundary at infinity, and I could use ODE techniques to get very explicit descriptions of at least the linear solution to the resolvent problem, to the resolvent equation. And so I wonder what you could do with non-local. And if, I'm sure that's done nicely somewhere. I'm not sure what is the technique. So maybe Remy or other of you people that like non-local things and work with them, maybe you can find an example of that and how it's done. I think that's really interesting. But there's nothing, I didn't say that this operator was a differential operator. It can be any operator with these properties, which is fun. Okay, that's
Hi. Can I ask a question?
Yes, please.
Yeah, so for the thing that you wrote on the board, you have this bound for the resolvent and you get the DL bound for the V check. Where did you use that?
Oh, because we needed to know that the resolvent resolvent set was non-empty to begin with.
Oh,
And let's see, where else did we use it?
also just to show that it is not empty, so you have this.
So that I had closedness and other things, but what else? Let's see. You know, I think I really didn't use it other than that. I think you're right. For this proof, I think I only used the X to X bound.
Mm,
That's, yeah,
okay. Okay. Yeah.
that's a good sharp observation.
Thank you. Thank you.
Yeah.
Thank you so much.
Yeah. Anybody else out? Let's see, I guess I should look at you over here. Yeah. You don't look so good. Over here. Just like a projector. What, any other questions or remarks? That was a good remark. Yeah, thanks. Okay. Thanks everyone for coming and see you